encourage everybody to sit on this side. That way we can.
Yeah.
Yeah. Okay, good.
¿Qué tal? Buenos días. Vamos a comenzar. Primeramente, pues agradecerles su presencia. Para nosotros es un placer que ustedes estén por aquí, sobre todo acompañándonos con nuestro distinguido huésped, el profesor visitante, profesor Bruce Logan. Miren, antes de comenzar me gustaría, si ustedes pueden moverse para este lado, ¿sí? Ya después si se incorporan más personas, podemos ocupar aquella parte. ¿Sí? Quiero comenzar con una breve descripción del programa. Primeramente mencionarles que todas las actividades van a ser en inglés, entonces vamos a ver esta parte introductoria, pero les voy a hablar en español, después ya todas las actividades se ven en inglés. ¿Sí? Igualmente, pues yo soy Miguel Ángel López, yo soy profesor investigador aquí del Centro del Agua para América Latina y el Caribe del TEC de Monterrey, y nuevamente, pues bienvenidos. ¿Cómo van a estar el plan para estos 2 días de actividades? Como pueden ver aquí, el día de hoy y el día de mañana. Today and tomorrow we'll have 2 big keynote speeches. Vamos a tener 2 conferencias magistrales. From 9 to 10 and a half approximately, de 9 a 10 y media. ¿Sí? Después, later, we will have today a workshop. Después vamos a tener este taller de 10 y media a 2:30. We will have this workshop, the first workshop, from 10:30 to 12:30 approximately. Of course, during this, Professor Rogan will adjust the time based on his experience in such a way that you not become very tired. Okay? Tomorrow, also, we will have another workshop at the same time, from 10:30 to 12:30, before lunch. Okay? Between this conference and the workshops, we will have a break of 10 minutes approximately, in such a way that we can take a little rest and go to the toilet room and everything. And after the workshop, we will have the lunch break. And today, during the afternoon, from approximately 2, here is a mistake, we will start at 2:30, the workshop, okay? 2:30. So I will appreciate that you be on time in such a way that we can attend the program exactly at the time that we are considering. Sorry. So, tomorrow, after the third workshop, we will end the formal activities with the public. During that we'll have another private activities with Professor, but tomorrow approximately noon, we will end the activities with Professor Logan. So for me, as I mentioned, it's a pleasure that you will here. So please enjoy the talks of Professor Logan. I think it will be very interesting, and I hope also it will be very useful for you. Okay? Probably some of you are initiating in this kind of topics about material fuel cells, but probably others have already some experience. So please enjoy, and I hope this activity could be fruitful and useful for you. Before starting, I would like to introduce Professor Bruce Logan, and I will show you a very brief summary of his experience, very long experience that you can also read here in the screens. Professor Bruce Logan is an Ivan Puch University professor in engineering, the Stan and Flora Cape Professor of Environmental Engineering, and Director of the Engineering, Energy, and Environmental Institute at Penn State University. Professor Logan also is an editor of the ES&T Letters and a former associate editor of ES&T, both published by the American Chemical Society. He's currently conducting research efforts in renewable production and development of an energy sustainable water infrastructure. Dr. Rogan has mentored over 130 graduate students and postdocs and hosted over 40 international visitors to his laboratory. He's the author and co-author of several books and over 500 referred publications. Professor Rogan is a member of the U.S. National Academy of Engineering and a fellow of the American Association for the Advancement of Science, International Water Association, the Water Environment Federation, and the Association of Environmental Engineering and Science Professors. Professor Rogan is a visiting professor at several universities, including HIT, Tsinghua University, Dalian University of Technology in China, with ties to several other universities in Saudi Arabia, the UK, and Belgium. He received his PhD in 1986 from the University of California in Berkeley, prior to joining the faculty at Penn State in 1997. He was on the faculty at the University of Arizona in Tucson. Professor, it's really my pleasure and honor to share these activities with you. I really appreciate the effort that you made it, okay, to talk 2 days. I think it's a very hard issue, but I think the experience of professor teaching, he knows very well the importance of this kind of events. So again, it's my pleasure and honor that you're here, and thank you for sharing us your knowledge and experience. Your hall and the public is yours.
Okay. Gracias. Thank you. I need to change this.
Yes.
Just actually, I can't see it.
No.
Oops. Just.
10 seconds approximately.
There we go. Okay. So, buenos dias, and thank you very much for the nice introduction and for inviting me to come here today. I'm very pleased. I've not been in Monterey before, so it's very nice to visit this beautiful campus and facilities, and I really look forward to our discussions. I don't know how familiar you are with microbial fuel cells and these bioelectrochemical systems, so I will try and cover the topic in this talk a little broadly, but of course with some depth to provide understanding of opportunities and possible avenues of discovery. So I'm from Penn State University in the middle of Pennsylvania, way, way far away. That's what it looks like. So this is really a bigger, the bigger picture is energy, our environment. A lot of people are casting this between energy, food, and water. Certainly all those things are tightly interwoven, as well as the focus on climate change and the idea that we might have unlimited energy seemingly sometimes, but if it's derived from fossil fuels, that's a problem relative to climate change. And so really what we would like to do is pursue energy technologies that are renewable and of course avenues of providing things that we want in our lives without perhaps consuming energy, particularly within the water nexus. And so the traditional view of our water infrastructure is we get as much water as we can, we don't worry about how much energy we use, and then when we're done, we call it wastewater and throw it away. But in the future, it's not wastewater, it's used water. and it's water that can provide an opportunity for resource recovery. For example, extracting energy out of the organic matter in the wastewater, or recovering nutrients and using them as fertilizers. And the water itself, of course, is a hugely valuable resource for other uses. And so we don't look at it as a waste anymore. We look at it as a resource. In my research, I've been particularly interested in the energy sustainability of the water infrastructure and looking at how we can cut that cord between a power plant and a wastewater treatment plant so as to not consume so much energy, or maybe even to produce net energy at a wastewater treatment plant. So how do we do that? Well, we can look at, as I said, at things in the water. In the US, we use about 5% of our electricity on our water infrastructure, and that amounts to about 15 gigawatts of electricity for our wastewater infrastructure. This is clearly not sustainable globally for adequate water and sanitation. It's too much energy. And so we need to find ways to reduce that. And if you just think about the fact that 15 gigawatts of electricity is used, that probably means 45 gigawatts of primary fuel, oftentimes fossil fuel. So eliminating the use of that electricity could potentially save 45 gigawatts. A gigawatt is a 1,000, a gigawatt is, essentially a nuclear power plant or a very large coal plant. So we'd like to turn the wastewater into an energy source. Typically, there's about 4 to 10 times as much energy in the wastewater than we use to treat that wastewater. So if we can obtain only a fraction of that energy back, the wastewater treatment plant could become self-sufficient. So I'm going to talk about today about two subjects. Most of the time I'll be talking about this energy neutral or energy positive wastewater treatment. And then if we have time at the end, I'll just talk a little bit about nutrient removal and desalination, which are somewhat related topics. No microbiology in those, but of relevance to the sustainability of our water infrastructure. So the idea here is to take a wastewater treatment plant, which is conventionally primary treatment, particle removal, and something like activated sludge, and take out that activated sludge system, which consumes a lot of energy in aeration, and substitute in perhaps something like a microbial fuel cell, which can actually generate electricity. Now, we currently use about 0.6 kilowatt hours for every cubic meter of wastewater we treat. But as I said, there's a lot more than that in the wastewater itself. So, how much of this energy could we really get back? If we were to convert, say, 2 kilowatt hours per cubic meter in the wastewater into power at a 10% efficiency, that's about 50 watts per cubic meter that we'd get back. Now, that's not a lot of energy, but of course, as you have more and more thousands of cubic meters of wastewater, it actually starts to add up. And more importantly, we're not using this energy to treat the wastewater, so it becomes a self-sufficient process. So that's our goal. I don't think a wastewater treatment plant is going to replace a large power plant, but certainly we can remove the need for energy at that wastewater treatment plant, or perhaps one day produce net. I think right now we're looking at about maybe only 6 watts per cubic meter. So there's an opportunity for increasing that power production and increasing the energy recovery. So in a very basic sense, this is a microbial fuel cell, and I have one of these little microbial fuel cells that I'll pass around at the workshop. I won't do that here, but it's really about a simple device in concept. It's 2 electrodes with some space in between them that you bolt together in a container. So the bacteria break down organic matter that's in this water. They oxidize it to CO2. The electrons that are released go to the other electrode. Now, of course, when we eat food, we breathe, right? So we eat, we take those electrons and we transfer them to oxygen. Well, the bacteria are here on this electrode, so they optimally don't have that oxygen, but the oxygen reacts at the cathode. So we create that current That current, therefore, can power some sort of load, a light bulb, a fan, a pump, whatever that is, and create useful energy. We can also take the same system, here shown with a membrane in between the two electrodes, and instead of having oxygen here, we can add a little bit of extra power into the system, and instead of reducing oxygen, we can reduce water, reduce essentially protons, we can produce hydrogen gas. So this is electrochemical hydrogen production, but the source of electrons is organic matter. And because we use organic matter as a favorable reaction as opposed to an unfavorable water splitting reaction, the energy needed to do this is a small fraction of what's needed to split water. In my talk tomorrow, I will talk about microbial electrolysis cells. Today, I'm mostly going to focus on microbial fuel cells. But in the general scheme, these are called microbial electrochemical technologies. They're electrochemical systems if it's just a study, but a technology if it's doing something. They can have microbes on the anode or microbes on the cathode, or both, but there has to be microbes on one of the electrodes to make it a microbial system. Sometimes we generate power, like in a fuel cell. Sometimes we add in a little bit of power to create hopefully valuable products, such as hydrogen or maybe methane. And there can be a membrane here or no membrane, or there can actually be stacks of membranes in different configurations. And so I'm not going to be able to talk about all those today, but I will talk about the importance of a membrane, particularly tomorrow. So you have, say, this, in this case, it's a very highly porous 3D structure. This is a brush. And you have microbes that grow on that brush. And the ones that can break down organic matter and make electricity, we call them exoelectrogens, out to transfer electrons outside the cell. They do that by either making direct contact with the surface. Some microorganisms can produce nanowires, electrically conductive filaments that convey the electrons from the cell to the electrode. Some produce mediators or chemicals that shuttle the electrons between the cell and the surface. And within these communities, there's always other microbes that just kind of live off the exoelectrogens in terms of breakdown products, or maybe they ferment substrates for the electrogenic microorganisms to use. So this is a figure out of a paper that is going to be published shortly in Nature Reviews Microbiology. And what we show is that there are microorganisms from all three domains of life, from bacteria, from archaea, and from eukarya, that can produce an electrical current. So it's really remarkable that microbes from such diverse, with such great diversity, can produce an electrical current. They don't all do so well at making high current. And so this is a log graph, so you can see that there are some here in the thousands of milliwatts per square meter or watts per square meter. There are some that only obtain less than 10 milliwatts or lower. So they vary greatly in what they can produce in terms of current, but still that ability is inherent in many different microorganisms. To understand in our microbial fuel cells, like this little one here, what kind of microorganisms typically evolve in these systems, we took two very microbially rich samples. This is two different wastewater treatment plants, and then from a natural bog area, which is very rich in microorganisms related to primarily methane production, actually. And we took those and we inoculated 3 different sets of reactors, 2 from the wastewater treatment, 1 from this bog, and we studied the voltage that was produced, the maximum voltage when we placed an acetate medium into the reactor. And this is the maximum voltage each time we emptied out the reactor. Each cycle lasts about a day or 2. And so you can see the natural samples jumped up very high, very fast in voltage and sustained that, whereas the 2 wastewater treatment plants were slower to get there, and they looked like they would not ever reach that same level, but over time they actually converged in power production. So we wondered, is this a convergence of microbial community as well? And the answer is yes. Most of the bacteria in these 3 different types of reactors, BOG and the 2 wastewater treatment samples, are all delta proteobacteria. And of those delta proteobacteria, nearly all of them were identified as Geobacter species, and primarily Geobacter sulfuriducens. So incredibly, no matter what the source is, and with all these different microorganisms, in this system, when we fed it acetate, we get Geobacter. In more complex systems, this is not my study, it's a study that was done by Sunichi Ishii when he was at the Venter Institute. They looked at MFCs that were fed domestic wastewater, and these are much more complex environment, much more complex communities. But the distinguishing thing you see here is still there is an abundance of these delta proteobacteria, which by and large are Geobacter, but because the substrate, the organic matter that they break down is so much more complex, you need a much more diverse community to break it down. If you fed the reactor glucose, you would need microbes to break the glucose down into acetate, and then the Geobacter to acetate. So as the substrate gets more complex, so do the communities. So I won't talk more about the microorganisms. Obviously, there's a lot more to talk about in that way, but to move into the technologies part, let's think about, okay, these microbes are there, they're going to grow, they're going to make electricity. How do we design a reactor to actually make use of that capability? And so it depends on certain materials. They must be inexpensive. It depends on an efficient architecture. And I will say that one of the primary requirements is enough cathode area per volume, because the cathode tends to limit power production. Not the anode where the bacteria are as much as the cathode. Both are important. The cathode's more important. So a number of years ago, a group out of Wetzus and Wageningen in Europe did a study, a couple studies, and basically they concluded these electrodes need to be less than $100 or 100 euros per square meter. That's very inexpensive. And you know, what are the components that go into this? Well, let's ignore the tank for a moment and just say we have wastewater. We're going to have an anode where the bacteria grow. We're going to have a cathode where oxygen reduction occurs, so we have to provide a route for it to contact air. But we don't want the water to leak out through the cathode, so the air has to get in, but we don't want the water to leak out, so we put a diffusion layer there. Then we want to bring the electrodes close together because that reduces what we call the internal resistance. That is, it makes it easier to produce more power. And then we don't want the electrodes to touch, and a lot of times we want to keep the microbes off the cathode, so we put in what we call a separator. Now the cathode in these original systems was made up of carbon cloth, a platinum catalyst, and a Nafion binder. The Nafion binder is almost as expensive as the platinum. So clearly, when you add up the cost of all these things, it's very expensive, over $2,000 a square meter. So clearly, this was not going to work. So we had to become more innovative in reducing costs. And I think we've really succeeded in doing that. We've, through advances so far, we have the cost of the materials to maybe $30 or $40 a square meter. And that doesn't say we can make them for $30 or $40 per square meter, but at least the costs are low. And so we always need to keep in mind as we improve these materials or performance to keep these costs very low. So how do we do that? Well, the first is to provide a lot of surface area for microorganisms without it costing a lot of money. And so we came up with this idea of graphite fibers wound with a current collector so that we have a huge amount of surface area for the bacteria to grow on. So these filaments are all spread out, and they're about 6 microns in diameter. A bacterium is about 1 micron in diameter, so a good surface area to size of microbes. And they can be made very cheaply. The cathode was more difficult, but it turns out that activated carbon is a good oxygen reduction catalyst at low current densities. And that's great because environmental engineers love activated carbon. We use it all the time to absorb chemicals. It's cheap. It can be made from a lot of things. And so we showed very early on that this cathode, which this one was actually made by Vito in Belgium, produced almost as much power as a cathode with a platinum precious metal catalyst. It's pretty amazing. So over time, we've tried to improve the cathode and the catalyst on the cathode. This is some work that we did recently using a mixture of iron, nitrogen, and carbon, which we pyrolyzed onto the surface. And you can see the activated carbon plane, which is about what platinum does, was elevated from about 1.5 to 2.5 watts per square meter. If we go to a more conductive medium, we can get up to nearly 5 watts per square meter. Of course, if we go to wastewater, and I'll be talking about this more, the conductivity of the wastewater is very low. The ion concentration is very low, and so because of that, we just can't produce enough power. Even though the catalyst itself is better, the solution conductivity limits that power. And so you can see the power here is double that which we get from platinum. But it's still quite low under more optimum conditions of higher conductivities and better substrates. So we have these little cube reactors. We want to make them bigger. How do we do that? For an engineer to design a system, we need to understand it better. And so how do we understand the components and how they're functioning and how they're put together? And so that means we have to come up with some sort of optimal infrastructure or architecture, but we need to think about where the resistances are, where the limitations are in designing these systems. So this little cube reactor, it's about 28 milliliters. It's like a teacup of liquid, not a coffee cup. I've seen some really big coffee cups at Starbucks. So this is a teacup. And, you know, this is this up. And so as we go in size, we look at the current density, current per square meter. And so if current is in current per square meter, then resistance has units of ohm meter squared. And so that means that if current density is staying the same as we get bigger and bigger, the resistance is staying the same. However, if we just use current, as we get bigger and bigger, it implies resistance goes down. So we have an area resistance. And this is not prevalent in the literature. And so it's a very new way of thinking about microbial fuel cells anyway. But I want to say that for the engineer to scale the system, we need to think about ohms meter squared. That is the resistance and the area of our electrode. So depending on your background, electrical circuits may not be something you're very comfortable with. I'll try and make it very simple. This is like the battery, right? This is how much energy you have in the system. There's the internal resistance of the system and then the external. So this might be the light in the flashlight. This is how good your flashlight is, the internal resistance. And this is your energy source, the batteries. And so in a microbial fuel cell, these are the chemical reactions that are producing power. These are components of our system where if we get them small, then the device itself doesn't suck up a lot of the power. And then we have more power for our external load. And so this is a paper that we've just submitted to do this, to talk about this, but we can break this down into our anode, our cathode, and our solution, and our membrane. And by doing that, we now know what's limiting the power. Is it the anode? Is it the bacteria? Is it the cathode? Is it the solution? How much do those things change? So the way we evaluate this system was we run a power curve, which means that we put different resistances in the system, and as we put higher and higher, as we go to lower and lower resistances, okay, the current goes up and up and up. Less resistance, more flow. Less resistance, higher current. So this is what we call our polarization curve. And if it intersects here, where the chemical thermodynamics says it should, it's a perfect reaction, but it never is. There's always this drop-off with the system, and then we tend to get a very straight line. And if we take the slope of cell potential and current density, volts over amps per square meter, that is ohms meter squared. The slope of that line is a resistance in ohms meters squared. So by fitting that line and by using this intercept, we can exactly predict this circuit. And these diamonds are measured power densities, and the line is what we predict based on this slope and this intercept. So we can now say, okay, we can reproduce that power density curve based on this internal resistance. And it works really well. We can predict the maximum power density, in this case, about 1.7 watts per square meter. Now we take the next step, and we want to break it down into these individual ones. And so we put a reference electrode near each electrode, so we know the potential of the electrodes. And now when we're doing that polarization curve, we just measure the potentials of the anode, the potentials of the cathode as a function of current. And based on this slope, we have a resistance for the anode. On this slope, we have a resistance for the cathode. And now we know the components of the system. We know what is limiting our power production. We can calculate the solution resistance just based on using a conductivity meter. So with this equation, and if you're around for the workshop, I'll tell you more about it, but with our conversation here, let's just say, okay, we know how to determine these individual resistances. What can we learn from that? That's the point here now. So here's what we can learn. I want you to look at the anode resistance, the cathode resistance, and then the solution resistance. And this is with two different electrodes. This is with this highly three-dimensional porous brush, and then this is with a flat anode. So carbon felt or carbon cloth or something like that. Now, you can't put this anode next to the cathode because oxygen leaks in and you don't generate any power. But with the brush, it can be very close to the cathode. And that's why this brush produces a lot more power than this felt. If you look at the anode resistance, these are in milliohms meters squared. These numbers for the anode are pretty close. So whether it's a brush or it's felt, it produces about the same amount of power. The cathode, yeah, pretty close. Again, these are a little bit bigger. But look at the solution resistance, 43 versus 14. These produce a different amount of power because we kept the electrodes widely spaced. If we bring them together, we get rid of that solution resistance, we can produce more power. And so you see that we produce 1.2 watts per square meter in this brush one, but only 0.7 watts per square meter in this one. And it's not because of the electrodes, it's just the electrodes are too far away from each other. In fact, you can see that if you look at these anode potentials, this is the brush, and this is green one is the felt. You can see that they're pretty close. They only start to diverge right out here, and the felt doesn't go as far because all that energy that it's making is being sucked up by this ohmic resistance. It's these electrical losses in the liquid. The ions just can't get between the electrodes efficiently. So this is kind of interesting to us because for many years we thought the felt just was really bad. But it's not really bad. It's not bad at all. It's just too far away. In fact, if you move the brush far away, you get the exact same result that it doesn't work as well, but the electrode potentials don't change at all. So this anode, both anodes work exactly the same. But if we move it far away, just like the felt, we get less power. Now, the big thing for us is we'd like to get out of the lab and actually treat wastewater. We want to make electricity from wastewater. So what happens when we go in this nice brush electrode system from phosphate buffer and acetate and this, well-buffered, nice, non-fermentable substrate like acetate, when we go to real wastewater? Well, lots of things change. First of all, the solution resistance goes from 14 to 98, right? I haven't changed this distance. It's just the wastewater is so non-conductive that we immediately increase the resistance of the solution by a factor of about 7. And then we see that reflected in both the anode and cathode resistances. They both go up as well. It's not just that the solution becomes less conductive, it's also that the electrode performance decreases as a function of that system. Now, I haven't proven here whether the substrates impact this, but the conductivity certainly is a big change. Okay, so now we say, all right, we understand these electrodes, the distances, and spacing is important. So how do we make a real microbial fuel cell? And these are a bunch of different designs that people have done around the world. I'll talk in the lecture this afternoon about scaling up systems. I'll talk more about these different designs, but basically what we started with was something like this. 2 bottles, a membrane between the 2 bottles, or even a salt bridge. This is not how you make a big system. You can't make one big anode and one big cathode. It doesn't work because the ions need to get between the electrodes. So you need to keep those electrodes very close and have no barrier between the 2 electrodes like you would in this system. So if you just want to study the microbes, this is fine. But if you want to build a scalable system, it has to be something like this. And so in our laboratory, as we've learned how to do this, we have our sort of generation 0. This is kind of where we started from with our first cube reactor. Then we started building slightly larger reactors with a few different brushes. Then we had arrays of brushes and multiple cathodes, and finally this 6-liter system which has multiple electrode arrays. This is the basic design. We call it a modular design. That is, we have an array of anodes that are all linked together. And then we have a modular cathode. You can take the cathode in or out. The cathode on this side, so it's 2 cathodes with an airspace. The cathode on this side works with this brush. The cathode on this side works with that brush, and so forth. And so the idea is we could mass manufacture these modules and then drop them into a tank. So here's a sort of a schematic of what this might look like at larger scale, and going from this laboratory reactor. And I'll talk a little bit about this single module that is about 1 meter wide by 2/3 of a meter high. So we said, okay, the cathode's the real critical step. How do we make a big cathode? And the problem was nobody knew how to make a big cathode. And so we talked to some vendors all around the world to try and get somebody to build us a bigger cathode. And we got 2 companies that offered to build us bigger cathodes. We tested each one, and only one of them actually could retain water. The other one leaked, so we couldn't use that one. And then we said, can we predict what's going to happen in this 80-liter reactor with, say, what was going on with this 28 milliliter or 240 milliliter area where all our electrode surfaces are changing? This is the cathode that we finally selected. It's made by Vito in Belgium. And it's kind of like a window. That is, each one of these panels is catalyst, which is connected to a metal frame. And so if you go to the center of this catalyst area here and you touch this corner here, there's almost no resistance because the electrons can flow along the metal pathway. Whereas if you made this out of one big piece of cathode, it would have very high resistance. So this was a nice design. This shows you the catalyst on one side. On this side, we have a diffusion layer, which is PTFE, sort of like Gore-Tex or Teflon, and that prevents the water from leaking out. So we can put this side against the wastewater and that side against the air. Based on our little tests, we looked at what happened when we went from 7 centimeters squared to 40 centimeters squared of cathode. We saw a drop off in performance. So we said, okay, let's assume on that basis what'll happen with the bigger one. It'll look like a lot of these littler ones. And so we said, we'll take this electrochemical data, and we get this just by running current through the cathode, and we'll match it with some real MFC data, because we say, well, the anode should work pretty much the same at smaller, larger scales, and see if we can predict the performance. It worked for these 2 little reactors. It didn't work so well for the really big one. So here's the really big one. You're looking at sort of a plexiglass front. This is the air chamber. So the idea here is the air is over here, the cathode's here, and the brushes are here with wastewater. And so you put the cathode right on the surface with the outer part removed, and we put a separator here to keep microbes off the cathode. We then, you can see this flexes out a little bit, so we had to bolt that to the module, and then we connected up the anodes. And you get something that looks like this. This is looking visually at the anodes in the reactor, 22 anodes to cover one big cathode. These are big, long brushes. If you have not enough brushes to cover the cathode, you get this much power. If you then put more anodes in there to fully cover it, 22, you get more power. And if you shrink the distance between the anodes and the cathode, you can get just a little bit more power. We got about 100 milliwatts per square meter, which is about only 20 to 25% of what we get in our smaller reactors with wastewater. So not perfect, but a good first start. But with this data, we can now look at how well did our components perform, looking at our very tiny reactor, 28 mils in wastewater, and our big reactor with wastewater. You can see the solution resistance here is actually pretty similar. In fact, these tests we did here with wastewater, the solution resistance was 118 milliohms meter squared, and actually it was a little bit more conductive in that actual wastewater we did these tests. So the conductivity was actually a little bit better. You can see the cathode here was the real problem. Its resistance went up by a factor of 8. And so while this cathode design is good, the resistance of that cathode still increased, and so it did not work as well. The anode actually only decreased in performance by a factor of 3. So this is great. This is nature versus engineers, right? The bacteria, they do pretty good when they get scaled up. The cathode that we make, not so much. So nature's pretty smart. Those bacteria have been, over 1 billion years perhaps, have been developing to be efficient at what they do. But when we put our cathode in there, it doesn't do, it limits performance. So improving that performance of the cathode becomes very key in terms of increasing the performance of the system. Okay, so let's see, we're good. We're 45 minutes into it or so. Okay, so now I have a question to ask you. I've been talking all about this power. Let's put it on human terms. Okay? Yeah.
You provide some numbers when you are describing different elements in terms of the resistance of the cathode and so on.
Yes.
But my question is, when you try to speak with the electrochemics community, they will right away jumping in you and telling why you don't use, for example, the randomless circuit when they actually consider very relevant the capacitance of the electrode. And I don't see that in your models. So also,
before you go too far, So one of the questions is, why isn't there capacitance in the system? And the answer is because we're under steady conditions where the capacitance of the system does not impact the steady performance. Capacitance will impact non-steady performance. Right? Because the capacitance is just to build up to a certain amount of charge, right? And then you were discharging it over a circuit. And as you dynamically discharge that, the capacitance becomes very important. But as you have just steady conditions, the capacitance, I would argue, is not as important. So that's number one. What was number two?
For example, when you study overpotentials on any cell or chemical cell, usually there is a overpotential by concentration, activation, and then the ohmic drop.
Right.
However, when you mention the overpotential of the anode, are you referring that, for example, the overpotential of the anode, you are under that term consider together the overpotential by concentration and activation? Or
okay. So there, for the audience, there's three different cases. One is the activation energy, which is usually a rapid drop. Two is an ohmic loss, which is very linear and where most systems operate. And then the third is at very high current densities, you see concentration losses. Okay? We hope we don't have concentration losses, but we could be in that range. But certainly, our anode potentials are incredibly linear. In fact, we don't even see an activation over potential. I could scroll back. I won't do that right now, but they're incredibly flat. That drop that we see is all the cathode. And so the bacteria actually are trying to push out those electrons, and there's no barrier at that point. It's very, very linear when you look at it. So we're pretty much in the ohmic resistance area completely for the microbes, but we do have the activation area and losses for the cathodes. And you can see this right here, actually. This is where we should be, but we're not. And this area may actually, in the large electrodes, be mostly in the activation area. We're not maybe even truly in our linear ohmic loss. But look at this. It's a perfectly straight line. Those darn bacteria, once again, they do pretty well. Yes?
What is the best? Feces, urine, or the more jumping in the water?
I didn't understand. What's better?
What is better in the water? Water with
Oh, feces or urine? Feces. The problem with urine is that it's mostly ammonia, ultimately, urea, then ammonia. And we don't know how to get high power densities out of ammonia in these systems, which is pretty amazing because ammonia has a lot of energy. But microbiologically, it's been very difficult to extract that energy in terms of power production. There are a few studies that have shown that. So really, all we're extracting is the organic matter energy. And in fact, I'll talk a little bit about trying to recover that ammonia so we don't have to make more ammonia, really. That's the energy saving. Yeah. Okay. Yeah.
Have you ever tried some biomimicry methods to try to mimic nature to obtain more amount of energy?
So one way we could do that would be a biocathode for oxygen reduction, something that facilitates, bacteria aren't catalysts. They derive energy. So we can get them to function, but so far nobody's got it to work better than these activated carbon catalysts. You lose power, you lose some energy. But don't stop thinking about that. There may be other opportunities. Good.
asking if in case of urine, it is better, for instance, mixing the urine with feces in such a way that the biological process could be similar to the wastewater treatment plants, where there is a mixture of nitrogen and organic matter.
Nitrification and denitrification in wastewater treatment plants is a pretty efficient process. So far, we have not seen that we can get both organic matter removal and ammonia removal at the same time. Ammonia stays very, very constant throughout the whole treatment process, except to the extent that it might increase due to release of nitrogen from the organic matter. So maybe in the future we'll figure out how to make that work, but as of today, not so much. So, can I?
Question.
Okay.
You mentioned that one important issue to improve the power generation is the resistance, the solution. Okay. Have you ever test different ways to increase the conductivity in the solution in such a way that you can reduce the ohmic resistance?
Yeah. So we could reduce the solution resistance by making water more conductive by adding in salt. So quite simply, if you had a brine, you could add in a very small amount of brine. You cannot go much above typically 20 millisiemens per centimeter in conductivity, which is about equal to a 200 millimolar phosphate buffer, which is about a brackish water, because then the bacteria, it's too salty and they die. So a few percent of salt and they die. But it does improve performance due to that conductivity for sure. So if you're on an ocean and you're at a wastewater treatment plant, you could pull in a little bit of seawater, make it work better.
Yes, I am asking you because one of the things that we were testing and proving is that in the conventional microfluidic cells, of course, in the cathodes, normally you can use water or oxygen. But in our case, we replace the water or oxygen by using a solution of hydrochloric acid in such a way that this hydrochloric acid increases the conductivity and also has several benefits because the degradability of the organic matter increases in such a way that we increase tremendously the amounts of energy that we can produce.
Yes.
And also another innovation that we introduce is we operate the system under vacuum. And we observe very good performance under vacuum and also combined with the hydrochloric acid as electrolyte in the cathode chamber. Later I will show you the paper.
No, I understand. I understand. The issue about using an acidic catholyte is that it takes energy to produce an acidic catholyte. Sulfuric acid, hydrochloric acid. If you have a waste stream available, it definitely is a big help, especially with microbial electrolysis cells. Because if it's acidic enough, it makes the reaction thermodynamically favorable for hydrogen production, where it's unfavorable at neutral pH. So I agree. There are definitely ways to make it work better. So I want you to think about this question for a minute here, because power densities are abstract numbers. I want to put it on a very personal note, okay? Every day we eat food, whatever units you want to use, megajoules, calories, kilocalories. Okay, so the food you eat every day, the question is, how many 100-watt light bulbs could you power based on the food you eat every day spread over the whole day? How many would you guess? 1, 3, 5, 10, 50, 100, 1,000, 1,000,000? Okay, I'm guessing 1,000,000's not right. But without making the calculation, I don't want you to make the calculation. Think think of a number. Does anybody want to say that number? Because I'm hoping you say a number that's wrong and not right, actually. 15. 50. Anybody else? Good, I love that number. 100. Better. They're not correct. They're going in the wrong direction. But that's the disconnect between food, your energy, the energy that powers you and what you can do, and our infrastructure, which is made of lights and cars and everything else. Just one. One 100-watt light bulb. I hope you never leave a light bulb on again thinking that light bulb just consumed all my food today. Or you could say, can we power the planet by food, by cellulose? No, we can't. We can't grow. We use 100 times more energy per person than that in a highly industrialized society. We can't do it. So we can't expect also, therefore, to power our homes with what goes down the toilet, okay? The BOD we produce is about 25 watts. So we eat, 2,000 calories. We release about 25% of that as organics in the wastewater. So you're not going to power your home with 4 people. You're going to power a 100-watt light bulb at best and less than that. So don't set your sights too high. What have we really done in terms of power per area? That's just how many electrodes we have, the area of the electrode. And then how much area of electrodes do we pack in per cubic meter? That's going to tell us how much power we get per volume. And so the best we've ever done is about 4 watts per square meter and 700 square meters per cubic meter for about 3 kilowatts per cubic meter. But that was only done in a reactor that was about 20 milliliters in size. As we go to bigger reactors and more realistic electrode packing densities, because this thing would clog in a heartbeat if you tried to put water through it, wastewater through it. As you actually get into wastewater and the kinds of systems that we've tested, which are about 25 square meters per cubic meter, we're looking at something like 6 to 10 to maybe, hopefully, 50 watts per cubic meter. These are the kinds of things which should be realistic expectations. And the numbers aren't big, but think about the food you eat. That's what's going to the treatment plant. So you have to be realistic. Now, that doesn't mean on an industrial scale that we can't engineer this for specific substrates more effectively, but at least in terms of domestic wastewater treatment, it's not going to be a powerhouse. But again, getting back to my original statement, it's hopefully not going to consume electricity. Now, there's another important aspect to this, and it gives me an opportunity to introduce another technology. The situation is that we need to treat the wastewater to get the COD less than about 60 milligrams per liter, BOD about 30 milligrams per liter, and we can't get down to 30 or 60 milligrams per liter very effectively and make electricity. There's just not enough food for the microbes to make the kind of power that we want. And we need to remove nitrogen. We talked about the ammonia. It's in the wastewater. It's not coming out in the MFC. So we need to think about how we're going to get it out. So this is a graphic just to show you is the COD. This is with 2 different resistances. This is with acetate at a high or low resistance, and this is wastewater. You can see as the COD gets lower and lower, the power is pretty constant. And then all of a sudden, it just drops down sharply. Once we get in here around, about 100 milligrams per liter of COD or so, the power drops off very fast. And that's just because of mass transfer. It's due to concentration effects. It's due to Monod kinetics. It's due to many things. It's something that we're going to have to deal with. And so there's a really nice technology developed by Perry McCarty at Stanford and another group of researchers in Korea. This is a fluidized bed reactor for wastewater treatment, and then it's followed by a hollow fiber membrane fluidized bed reactor. This reactor filters the wastewater and produces a very high quality permeate suitable for many reuses. And so instead of using this first process, we decided to use a microbial fuel cell. One of the things with this process is it converts the organic matter to methane, which can be dissolved at higher concentrations when the wastewater is cold. And so the methane recovery is a challenge. But we said, well, what if we take this hollow fiber membrane reactor and we put it on the effluent of our MFC? Wouldn't that produce a good quality wastewater? And this is, whoops, let's see if I can get this graph, this thing to run. You can see these little GAC particles bouncing around in here. And go back again. And what's happening is the water is being recirculated here, which keeps these granular activated particles suspended. And then we apply a suction to the hollow fiber membranes, and we pull the wastewater, the treated water, through the membranes. And so schematically, it looks like this. It's just some hollow fibers where the wastewater's here, it's being pulled through here. The organic matter, as it comes into this reactor, tends to adsorb to the activated carbon particles. So it very quickly comes out of solution. It's degraded on the particles. And then the water, which now has very, very little organic matter in it, can be pulled out through the membranes. And because these activated carbon particles bounce against these hollow fiber membranes, it doesn't foul. It can go a year or 2 years without appreciable fouling. This is an amazing technology. For a wastewater with less than 100 milligrams per liter of COD, it's a perfect technology all by itself. It really is quite amazing. So we hooked that up to a microbial fuel cell, actually a couple of microbial fuel cells to feed to one of these reactors. And our effluent was 16 milligrams per liter of COD out of that membrane reactor. That's very, very high quality. Almost no total solids because it's all been filtered. No clarifier needed. It's a beautiful process of both making electricity in the MFC and effectively removing the remainder organic matter in the AFMBR. We've done a little bit more work. I won't go into this too much, but I've looked at the sort of the hydraulic retention time. The hydraulic retention time is only about an hour in one of these systems, which is quite short. We thought, well, maybe it would work better if we went to longer retention times. No, that's not true. It's actually an hour is fine because the absorption of organic matter is very fast onto that activated carbon. And so pretty much no matter how you load it, as long as you don't load it too much, it will work pretty well. And so, you know, at 100, 150 milligrams per liter of COD going in that system, it works very well. So this is where I'm going to conclude the first part of the talk. Maybe I'd like to say that, and I'll go to the next slide before I ask for some questions again. But you know, we have modular designs. We have bacteria that can do a pretty good job. It doesn't mean that we can't help them do a better job on the anode. That's something we'll talk about later on if you're around. But we have to recognize that we can't do everything with just a microbial fuel cell. If we're really going to treat the wastewater, we're still going to need a secondary process. This is one that's good. We're looking at other ones that we could do this as well. Ultimately, to make the full system work, we also need to think about nitrogen and phosphorus removal. Phosphorus removal can be done chemically pretty efficiently, but removing ammonia is somewhat difficult. It can be done with Animox, which is a very finicky process, shall we say. And you don't actually recover the ammonia, you destroy it. Same thing with nitrification, denitrification. You destroy it, you don't recover it. And so, I have about another just 10 minutes or so talk about nutrient removal and actually desalination, because it's a technology related to that. But maybe I'll take a break here and say, are there other questions that I can answer now before we finish up that piece?
I would like to make some comments in respect to what the professor is talking about in the last part. That we think that one of the main purposes is to treat wastewater. Okay? And additionally, it is possible to produce electricity or water energy. It's a plus that we can obtain. Okay? So that's why what the professor mentioned, that necessity to remove organic matter, to remove the nitrogen and phosphorus from the wastewater is probably the main purpose of the cleaning of wastewater. Okay? So what we are looking for is to in some way to recover some of the energy that is available in such a way that we can make more sustainable the system in the future. Okay? So that's why this issue is very important.
And I would add, I have focused on domestic wastewater treatment, but consider an industry, particularly one which is food processing, maybe something with a lot of sugar in the wastewater or something like that, where this would work very well because higher concentrations of organic matter, not a lot of particles. So there are opportunities outside of just domestic wastewater treatment, but I've focused on that just as a general, more widely applicable technology. Well, so far, up to the scale of 6 liters. As you see from the bigger reactor, that cathode is about 0.7 square meters in size, so about a meter wide by about 2/3 of a meter high. It's not doing as well as we'd hoped, but it's certainly working. And so if that design is translated to just many, many more modules, it's scalable. We have a modular size that should be inherently scalable. But that remains to be seen whether it actually works when we do that. So we're building a bigger reactor to try and test this at a site. Yes, you're welcome.
I have a question about the microbial population.
Yes.
When you use wastewater, you have organic matter that may promote the growth of archaea, methanogenic bacteria.
Yes.
And that will lower your power, I guess. I don't know. How do you handle the growth of these bacteria that you don't want?
So some studies have been done between, for example, Geobacter and archaea when they're competing for acetate. Geobacter wins.
Wastewater, you have a lot of concentration of acetate. You make sure that that happens.
So when you actually get the wastewater, it's the bacteria competing for the complex organics to break them down into simpler organics, and then it's the electrogens and the archaea and everybody else trying to get those simple molecules. So that's where the competition becomes. And if you load the system too high in COD, too much pounds or kilograms of organic matter per volume, you get a lot of methanogenesis because the bacteria can't produce enough current to pull that away. If it's lower, then the bacteria win and the methanogens really, they get outcompeted.
So I guess for microbial fuel cells to work, you have a great concentration of acetate.
Or something that can be converted to acetate efficiently and not too high in organic loading. So if you have a COD of 1, 2, or 5, 6 grams per liter, it's okay. But if you go 5, 10, 20 grams per liter, you have an anaerobic digester. That's all you're going to have. It's too much organics to process through a circuit, and you just get a lot of methane. Yeah, it's a good question.
And I wanted to ask you, because especially one of the problems in the wastewater treatment plants is how to manage the sludge.
Yes.
Yeah, and one of the ideas we are trying to test is to digest this sludge by using microfluidics. But from this point of view, what you are mentioning, now I am wondering
Ah,
how could effective could be.
well, the sludge yield of an anaerobe is much, much less than an aerobe. So intrinsically, we should see a lot less sludge. There'll still be some aerobic degradation, but we hope to really shift that as much as possible to anaerobic and maybe cut sludge production in half or by 2/3. And since sludge handling is about 50% of the cost of operation, that's a really important number. So if you can make that more effective, it works. So to the extent that you succeed in directing all the current, the food into the current, directly reducing sludge. Yeah, it's I think, very important. Yeah.
What I notice about those numbers is that we can get much power from those batteries, or let's say,
Yep.
fuel cell. So to act in terms of the adversities or difficulties to try to get in something useful, I see that for me it's not clear if you are using those, if you are collecting those numbers by, let's say, continuous steam tank reactor or just like a batch system. And I am wondering if you have some strategies or have you thinking about how convenient can be to put some pumps to try to maintain stable, let's say, the chemical oxygen demand in order to have a almost stable signal of the current, but at the same time, we know that if we put in a pump, in somehow we are investing energy instead of collecting energy.
Yeah.
So after all, have you discussed some strategies since these systems are not, let's say, they don't provide too much power?
Yeah, so we have been looking at the impact of batch feeding versus continuous flow. We've looked at recirculation, and I can share some of that with you later in the talk, this last talk of the day. But you're exactly right. I mean, anytime you start investing a pump into the system, you are pulling away the energy that you hope to get back. So mostly we hope the system works best with just once through gravity flow, no need for pumping. We can get improvements with recirculation though. But by and large, I'm guessing, it's not a fact, that it's not going to be worth the energy. It's going to cost more to recirculate it. Do I have time to finish up this last part? I need 10 minutes. Everybody okay with that? Okay, because I'm moving around up here, but you're not. But I can continue on, or we can take a break. It's all up to you.
No, we'll take a break and we'll return at 10 here. Okay?
That's fine. Thank you. Should actually finish up this one first.
If you want some coffee or something, I can bring it for you.
I fortunately got a nice little espresso right before we came here,
Okay. So you're good.
I'm good, yeah. If I have another espresso, I might be jumping around a little bit too much up here.
Probably for the afternoon. Then.
Yeah, maybe after lunch, yeah.
Okay.
Yeah.
Thank you for your speech. I have not been involved that much in research. Right now, I am a biologist.
Okay.
I'm working on other water programs in the water sector,
Okay.
but this is very interesting.
Good. You know, it's never easy to know who the audience is, and when you're talking about microorganisms, the people that do chemistry are like, microorganisms. Then you're doing electrical circuits, and almost everybody's like, electrical circuits.
Yeah, I know. Well, I love microorganisms.
Yeah, all right. So try and put a little bit out there, but you know, the strange part is the microorganisms become somewhat uninteresting here in a way, because it's only when you really get down to the molecular scale of how they do it,
Exactly.
and that's really how to facilitate, say,